everyone, this is K Devender Reddy, Assistant Professor in Department of Electrical Engineering. In this video, we are going to discuss about constructional features as well as the principle of operation of synchronous motor. So let us look into the what actually the principle and the constructional features of synchronous motor. Generally, we know the motor which can convert electromechanical energy conversion device, which can convert your electrical energy as an input into the output as a mechanical energy. So there are several machines, several motors we have, like in AC as well as in a DC. Specifically, synchronous motor have some unique features than your induction motors as well as the DC motors. That is, the speed of the synchronous motor is constant irrespective of the load. It can run only at one particular speed, but whereas in the case of induction motors as well as the DC motors, we can control, we can vary the speed, and the speed regulation is much high in the DC motors and the induction machines compared to the synchronous motor. Where in induction motor, the speed of the induction motor will be vary depending upon the load offering on the induction motor. But whereas in the case of synchronous motor, it cannot vary the speed irrespective of the loading conditions, and it is run only at one particular constant speed. That is the unique feature of the synchronous motor. Let us look into the constructional features of synchronous motor. And generally we know the synchronous speed ns equal to 120 f by p. The only possibility to vary the speed of synchronous motor either to change the frequency supplied to the synchronous motor or by changing the number of poles. Only this is the way how we'll change the speed of synchronous motor. Let us look into the constructional features of synchronous motor. And here I am showing clearly this is a stator, that is a yoke part of the stator yoke, and inside we have a stator, and the stator having slots to hold your stator armature winding, the stator core having slots, and these slots are holding the armature winding. So these slots contains a three-phase either star or delta connected stator winding that is called an armature winding. Armature winding is holded in the slots of stator, and this stator will be connected to a three-phase AC supply or YB, phase sequence of the three-phase AC supply, which is connected to stator winding, whether it is a star connected or a delta connected, and the rotor, which may be of a projecting pole type or a non-projecting pole type. That is generally we preferred projecting pole, that is called a salient pole type of the rotor, and the rotor contains field winding. This is a field winding of the rotor, field winding, the field winding which is excited by a DC supply plus and minus polarity. And you can see compared to the other kind of the motors, the induction motor is doubly excited machine. There are two excitations are required. There are two kind of supplies are required. One is to supply the three-phase AC supply to the stator, and another one supply that is required for generating the magnetic field in the synchronous motor, that is by the rotor winding called a field winding, which is excited by a DC supply. There are two excitations required. So one excitation for a stator, another excitation is for rotor. That is why it is called as a doubly excited machine. And most of the cases, as we discussed, the synchronous motors are using salient pole or a projecting pole type rotor structures. And the rotor of synchronous motor is made with the laminations of a sheet steel. Generally, we know how we will reduce the eddy current losses as well as the hysteresis losses of the core by choosing a proper steel, that is a high grade silicon steel, as well as by properly laminating the stator and as well as the rotor as well. The proper laminations and their insulating each the lamination from other also effectively reduce the eddy current losses. That is why these laminations are very, very important, and the lamination thickness will be depending upon the operating frequency of the motor as well. So any kind of the machine, whether it is an induction machine or a synchronous or it's a DC machine, the lamination thickness is purely depending upon the operating frequency of the machine, which will be connected to a rated frequency. Generally, it is a 50 Hz frequency rated machine, where the lamination thickness may vary between 0.3 mm to 0.5 mm thickness. So the already we know about the salient pole structure rotors. In the salient pole structure rotors, the number of poles are high compared to the non-salient pole type or a cylindrical type of the rotor. If you required a high-speed synchronous motor, you go with a cylindrical rotor structure synchronous motor, where the number of poles are restricted to either 2 or 4. You can obtain maximum speed from the synchronous motor, which is of 1500 rpm, or even go to the 3000 rpm. But whereas in the case of projecting pole type rotor structure synchronous motor, the speed will be of less, because the number of poles are more compared to the cylindrical type or wound rotor type synchronous motor. But most of the cases we preferred salient pole structure because of its constructional features. It is very advantageous than non-salient pole or cylindrical rotor structure. And the whatever the remaining parts in the synchronous motor, which is very similar with the other machines, whatever the insulation media we used and the type of the slots we used, that is very similar with whatever the DC machines, induction machines, and similarly in the synchronous generator what we discussed, which is of very similar. But only the difference of the synchronous motor is a double excited machine. There are two windings. One is a stator winding called armature, and a rotor winding called field winding. And these two are excited by two different supplies. One is by three-phase AC supply, another one is by DC supply. Let us looking into the working principle, how the synchronous motor is converting your electrical energy into mechanical energy. And so you have to remember, the synchronous motor is a doubly excited machine. It requires two different supplies. One is from the three-phase AC, another one is from an auxiliary DC source is required for a synchronous motor to excite field winding. So here, when a three-phase supply is given to the stator, obviously we know whether it is a star or delta connected, it has to produce a rotating magnetic field. That rotating magnetic field will be available in the air gap. The air gap is nothing but the distance or space between your stator as well as the rotor object. So when you are excite the stator winding with a three-phase AC supply, which produce a rotating magnetic field. Similarly, the field moving polarities is known the rotating magnetic field. Similarly, the rotor is excited by a DC supply. When you are exciting the stator with the AC supply, three-phase AC supply, which producing a rotating magnetic field, right? With respect to the number of poles, the speed of the rotating magnetic field is depending on the frequency as well as the number of poles of the machine. And whereas in the case of the other side, that is a rotor structure, it is excited by a DC supply, and it is also producing a magnetic field which is of fixed polarities, the fixed poles like the north and south poles on the two sides of the projecting pole rotor. For example, if it is a two-pole machine, if it is a two-pole rotor, the two fixed poles, north and south poles, will be developed when you are exciting the rotor winding with a DC supply, and it is constant. It is a constant magnetic field is developed when you are exciting the field winding with a DC supply. The polarity of the AC wave changes, but whereas in the case of a stator structure, the polarity of the AC wave is changing with respect to the time factor, and it will be on for example, in the polarity of AC waves is changed on each and every half cycle. So when a positive half cycle and another one is a negative half cycle, in that particular way, the magnetic field also changes its poles according to the supply is given to the synchronous motor stator. But whereas in the case of the uh, rotor side, it is a fixed poles which is experienced on the rotor projected pole phases. One is south and one is north. So this is a case we clearly shown. Rotating magnetic field is developed in the stator, and a magnetic field developed by the rotor is a constant. Fixed poles are experienced on the projecting poles, that is north and south here, right? So when the stator and the rotor poles, both the same poles will come into the picture, where come each other. For example, this is a case when north pole of the stator and the north pole of the rotor will be face each other, come across then two similar poles are oppositing each other. The two similar poles are oppose each other, so there will be a repulsion forces will come into the picture, and the rotor will pulled into in a anti-clockwise direction. The rotor will pulled into the anti-clockwise direction, that is it is rotating in a or pulled back to the anti-clockwise direction when both similar poles are come across. And in the next case, when two unlike poles are coming into the picture, when two unlike poles are coming into the picture, for example, the stator poles are keep on changing. It is depending on the supply, that is it is depending on positive and negative half cycle of your sinusoidal supply. When it is changes from north pole to south pole, now the rotor will attract to the stator poles and it is pulled into the clockwise direction. It is rotating in the direction of the clockwise to attract the unlike pole like south. But this is will happen within the very fraction of time. It will the rotor will experience the anti-clockwise direction torque, that is anti-clockwise direction forces, as well as the clockwise direction forces within a very fraction of time. The rotor will subject it to the both the forces, the attraction forces as well as the repulsion forces on the rotor object within the fraction of seconds. So these two forces are equal each other. The anti-clockwise, that is the opposition forces, as well as the attraction forces, both are equal each other. Then the rotor will remain stand still. It will not affect it will not um, moving in anti-clockwise direction or in a clockwise direction. It will not affected by any of the attraction forces or repulsion forces. It remains a standstill because each of these two forces are equal in magnitude, and but they are opposite each other, that is in a different direction. So the resultant force acting on the rotor will be zero. So the rotor of synchronous motor will never rotate. That is why the synchronous motor is a not self-starting motor, which requires a starting auxiliary source, or whatever we call the some auxiliary machine is required to start the synchronous motor, and how we will see. So from this discussion, we conclude that the synchronous motor is a not self-starting motor. We need some starting method, or we need some we need some prime mover to start the synchronous motor. That is called, for example, when we are going to use one prime mover, whether it is a DC motor or induction motor, not an issue. So let us, I am considering one prime mover. I am taking one prime mover. It is connected to the synchronous motor rotor, the rotor of the synchronous motor, and another auxiliary prime mover which is connected to the synchronous motor. This prime mover will start the synchronous motor, and it is running with a rated speed that is nearly closest to the synchronous speed. So once the speed of the synchronous motor attains close to the synchronism, that is close to the rated speed, where unlike poles are attract each other, when the rotor of the starter, that is when the rotor of the synchronous motor is rotating and it is reaches to the almost synchronous speed, then at that particular point of time you have to excite the rotor winding with a DC supply. When it is reaches to the synchronous speed, or it is nearly equal to the synchronous speed, attains the nearly equal to the synchronous speed of the synchronous motor, so at that point of time you have to excite the rotor winding, that is with a DC supply, which produce a magnetic field, that is rotor magnetic field or field winding, which produces the north and south poles and the projecting poles. So the rotor of synchronous motor is rotating with an auxiliary device like a prime mover, and when it is reaches to the nearly equal to the synchronous speed, you have to excite the rotor winding with a DC supply. So where unlike poles are come across, it is pulled into the synchronism. Now the rotor is rotating with the synchronous speed. So when it attains the synchronous speed, that is, there is a magnetic locking between stator poles and the rotor poles. At that point of time, you have to disconnect your prime mover from the synchronous motor, and it is keep on rotating with the same speed of rotating magnetic field. That is what happened when it is nearly equal to the synchronous. When synchronous motor brings you to the nearly equal to the synchronous speed, the unlike poles are at a particular time will come across. It will be attracted by the unlike pole of the stator, and it is pulled into the synchronism. That is, there is a magnetically locking between a stator poles and the rotor poles. The magnetic locking between the stator poles and the rotor poles, that attraction force pulled your rotor into the synchronism, and it is keep on rotating with the same speed of rotating magnetic field, irrespective of loading condition. So when it is into the synchronism, you have to disconnect the prime mover which is connected to the synchronous motor. Now the motor will rotate at same speed as synchronous speed. Let us look into the some main features of synchronous motor. So we know it is not a self-starting device. The synchronous motor is not a self-starting motor. It requires some external device, an auxiliary device, to start the synchronous motor. And to synchronize the rotor with the stator poles, we need an external device, whether it is called as a induction motor, a prime mover, or else a DC motor. That is, there are certain number of prime movers available. Depending upon the requirements, we choose one of the prime mover for starting purpose of the synchronous motor. The speed of operation in synchronism with the supply frequency, and hence for constant supply frequency, they behaves as a constant speed motor. So the synchronous motor is um, running at constant speed, that is equal to the rotating magnetic field, irrespective of the load condition. Where you are increasing the load or you are decreasing the load, the speed of the synchronous motor will not change. This motor has a unique characteristics that is called as under any electrical power factor. It can operate under any electrical power factor. That is, we can use the synchronous motor as a synchronous condenser. That is under over excitation, no load category. The synchronous motor can act as a synchronous condenser to improve the power factor of your existing system. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.